In this video, we want to discuss a few more advanced concepts of sinusoidal functions because the other area where sinusoidal functions are widely used is in the area of signal processing. Now, at this point, most of you don't have the mathematics background for us to go into a lot of mathematical concepts of signal processing, but we will go through a few. But what I want to do is point out some conceptual things. And so there are a couple of algebraic and trig equations that generate some of the functions we'll talk about that you'll just have to bear with me and take my word for these functions because they come from a calculus-based derivation. So that's the only thing really that we won't go into is the calculus behind where some of these equations come from. So the first thing we want to talk about is how we would determine the parameters of a sinusoidal function given a graph. And in this graph, I will show on the next page, there are a couple of things that are specifically illustrated that we haven't talked about before. And one of those is going to be the concept of a DC offset, meaning the entire sinusoidal function is not horizontally centered around the y=0 axis. So let's look at the figure. So here's the figure, and you'll notice that, that it actually goes from -5 to 1. Meaning it's actually offset in the negative direction. And so when we want to obtain a mathematical expression for this, we add this term b here. So we have our normal sinusoid, which is a cosine omega naught t plus phi, where omega naught is the frequency in radians per second, b is the phase shift, a is the amplitude, and b in this case is going to be a vertical displacement, which basically adds a constant to this function, shifting the entire thing up or down. So from the plot, we want to determine what those things are. So the first thing to determine is to look at what is the amplitude and what is the DC offset. So the amplitude, you'll notice it swings from -5 to 1. And so basically we find this by just taking the difference in the maximum value and the minimum value and dividing by 2. So if we take 1 minus a -5 and we divide by 2 and we take its absolute value, we get 3. And so you can easily see, I mean, it's pretty visually obvious to find the middle of this sinusoid in this particular graph, but not always. So if you were given a graph that maybe had, some fractional components or something like that, and it wasn't obvious it went from 1 to -5, the way you'd find the amplitude is take the max, subtract the min, divide by 2. So you can easily see 1, 2, 3, that's our amplitude. And once again, remember, the amplitude is the value from it's basically half of the full swing. Okay, then we want to figure out what is the DC component. In other words, how much has this been offset from the x of t=0 axis? So in other words, was it shifted up or down? And in this particular case, it's we can find that by looking at where the center of the function is, which is at -2. So that means this entire sinusoid was shifted down by 2. So b is equal to -2. So we've determined the amplitude, we've determined the vertical displacement or DC component, it's -2. Now what we need to do is we need to find the angular frequency and the phase. So first, let's look at the angular frequency. If we look here, let's find, and this is in seconds, if we look here, if we go from -pi to pi, or a full swing of 2 pi, that's actually equal to 1, 2, 3, 4, 5 full repetitions of this function. So 2 pi then is equal to 5 periods, or 5 times t⁻⁻, where t⁻⁻ is the period. So the period is 2 pi over 5. Now, why would we go a full 5 periods? Well, in this graph, it's a little hard to read. For one period, it's a little hard to read what this time is. So because of that, we just kind of keep going until we find a place where it crosses just for this graph of vertical axis, and in this case it does that again at pi. So we go from minus pi to pi. There's nothing magic about minus pi and pi. You wouldn't necessarily do that for every problem, but for this particular problem, it turns out that that's a convenient choice. So 5 periods occur in a 2 pi time, so the period would be 2 pi divided by 5, and that's going to be in seconds. And then remember omega naught, the frequency is 2 pi over the period. So if we divide 2 pi by the period, we get 5 radians per second. So we can plug in omega naught. It's going to be 5 radians per second. Then finally, we need to know the phase shift. So the easiest thing to do for the phase shift is to look at a particular point on the curve. So if we look at the t=0 point, if we plug in 0 for t, then we have basically -2 for b, so that's what this is, and then omega t goes to 0, so we have 3 cosine phi -2. And how do we get this -2? Well, that's basically x of t at t=0. So find your t=0 point, and at t=0, the value of the function is -2. So that's going to go right here, -2. You know your amplitude. You know that t is equal to 0, so this is going to go to 0. So since x of t is known and a is known, then you can find the cosine of phi. And so you can find phi by taking the inverse tangent, or sorry, the inverse cosine. Now, once again, in this particular case, there's nothing completely magical about using t=0. It's a little bit convenient because it eliminates this part of the angle. In this particular problem, it's also convenient because that's where the function passes through the exact value of -2. But if it were a different function and it had a more convenient point to use, it's fine to use any point on the curve because the amplitude is known, b is known, omega naught is known, t is known. You can pull the value of x of t from the graph. So it just so happens that this one goes through an easy point. You can look here at pi. That would be a similar point. So you could have used pi for t, plug in your omega naught, and solve for phi that way. So it's just easier to use t=0 because it makes this whole portion of the angle go to 0. So that's how you would find from a graph the period, the frequency, the phase, and the DC offset and amplitude. All right, so the figure below just illustrates on MATLAB a plot of a cosine function, and I'm giving you the little code that I used. I didn't do anything fancy about this plot. I just selected t running from 0 to 10. The frequency that I selected, the omega naught, was 2 pi, and so I'm plotting 10 times the cosine of 2 pi t, plotting the time versus f1, which is the cosine function, and I get this graph here. It's important in MATLAB when you do a cosine function plot that you choose a small enough step size, otherwise the graph is going to look choppy. It's also important that you choose enough time to get a good representation of the function. But if this were too large, say you went to 100, then your function would just be, it would change so rapidly you wouldn't actually be able to see anything that was going on. So important on your plots when you set those limits on what you're going to plot or how much you're going to plot. Obviously, if we went from 0 to 1, we'd only get like this portion of the graph plotted. So you really want a good representation just for the viewer to be able to see what the plot looks like. So in plotting sinusoids, you might have to play around with how much of the sinusoid you plot to make it aesthetically pleasing to look at. All right, this is an example of a function with a phase shift. I think we've looked at this before. I've included more text as well as the MATLAB code that generates this so you can see what happens with the phase shift. This is a function of with two different frequencies. I think we've also looked at this one before. I plotted one on top of another so that you can see how the sinusoids of different frequencies plot out. This may be slightly different than the previous example. But what I want to show is this. All right, let's go back and let's look at what F1 and F2 are. F1 of t is 10 cosine of 2 pi t, and F3 of t is 10 cosine of 3 pi t. So I'm just going to take these two and add them together. And then, so this function that I'm plotting here is F1 plus F3, and it's going to look like this. So if we look at figure 4, we can start to explore some of the concepts of periodic functions and frequency content. Now, first of all, realize that this continues for negative time. I've just plotted it from 0 to 10 here, but you could plot it from -5 to 5. This is periodic for sure because it repeats and it definitely has a period. Judging from the figure, the period appears to be 2 seconds. So when you have a periodic function that consists of the sum of functions of different frequencies, you're going to generate you're going to have what is called a fundamental frequency. The fundamental frequency is 1 over the period of, in hertz, is 1 over the period of the net function. In other words, in this case, 1 over the period of F4, which we can see from the graph. In this case, you notice that that's 2, that t is roughly 2, and so F would be 1 over 2, omega naught, the fundamental frequency, would be 2 pi over 2, or pi. Now let's go back and look at our two functions. This one has a frequency of 2 pi. This one has a frequency of 3 pi. But back to our graph, notice the fundamental frequency is pi radians per second. So it turns out that the fundamental frequency is going to be a factor. It's going to be the greatest common factor of all of the frequencies making up the sum. So in other words, if I had 2 pi and 3 pi, the greatest common factor there is pi. If I had 2 pi and 4 pi, the greatest common factor is 2 pi. So it depends, the fundamental frequency depends on what we refer to as the harmonics, or the higher order frequencies, and what their greatest common factor is. So that goes way back to elementary school math, finding the greatest common factor of some numbers. All right, we'll look at that some more. We'll look at examples of the fundamental frequency further later on in the course of these lectures. Okay, now what I want to talk about is, so we have this signal, and you remember that we constructed this of two different frequencies in hertz, 1 hertz and 1.5 hertz, or 2 pi and 3 pi radians per second, and it depends on what class you're in and what textbook you're using, whether people will refer to frequency in hertz or in radians per second. Now, based on how we constructed our original function, they each had an amplitude of 10. So there's another way to look at this that's kind of interesting, and that is to look at what is its frequency content. So in this case, what I'm plotting is I'm plotting the amplitude of each cosine function that makes up this wave versus frequency. So we had an amplitude of 10 in our cosine function that had a frequency of 1 hertz, and we had an amplitude of 10 in our cosine function that had a frequency of 1.5 hertz. So if we plot it in this way, we basically have a line at 1 with an amplitude of 10, and we have a line at 1.5 with an amplitude of 10. This is referred to as an amplitude spectrum plot. Spectrum means as a function of frequency, and amplitude, as you recall, is obvious. So from this plot, if we didn't know anything else, we would know that we have one cosine function with a magnitude of 10 and a frequency of 1 hertz or 2 pi radians per second. And we have another one with a magnitude of 10 and a frequency of 3 pi radians per second. So given that this was cosine functions only and that no one was phase shifted, we could actually, from this graph, plot the original function. Okay, so we could actually know what the components were. Now, there's a little bit of an issue if the components have a phase shift. If any of these components, and let's go back, if either of these functions contained a phase shift, we would not be able to fully regenerate the F4 from this information alone, because this information is only information about the amplitude. So you would actually have to have information about the phase if you were going to reconstruct the signal as it originally was. So in electrical engineering applications, we're often working with signals. They often have a range of frequency components present. So for example, if you're listening to my voice, the frequency range for my voice probably ranges primarily from about 200 to about 500 hertz. My fundamental frequency is probably somewhere maybe around between 200 and 250. That's just an estimate. And then there are components or harmonics, which would be higher frequency components of the fundamental frequency. So a harmonic is an integer multiple of the fundamental, always. So in listening to my voice, if you were to look at this amplitude versus frequency content, it would probably range from somewhere in the low 200s, and then there would be some higher frequency components, but most of it would be found, within a factor of 5 harmonics of the fundamental. And then there would be some noise components because certain sounds that we make in language sound noisy as far as the signal is concerned. So that would give you an idea, if you wanted to filter out background noise, of what the frequency content was in my voice that you were concerned about. Another application where frequency content is relevant is in graphic equalizers for your stereo. So if you're a fan of bass and you want to turn up your bass, what you're actually doing there is you're actually amplifying only a segment of the frequency content of the music, and that would be the lower frequency or the bass frequency segment. So it's important for various applications to understand what is meant by the frequency content that's present in the signal. This one is a very simple signal. It only has 2 components with 2 different frequencies and with equal amplitudes.